5 major reactions, and there's others, but those are the ones that we're considering right now. All along, we've just been using benzene over and over and over again to illustrate these reactions. Now, there are going to be a lot of times when you might have something other than benzene, and most importantly, you might have something else already attached to benzene, a group or a substituent. And now we need to think about 2 major topics when dealing with this. So we're going to consider, what about multiple, we'll call them substituents. And 2 major things to think about. One is the rate of the reaction, and then 2 is the regiochemistry. We'll define these terms here a little bit more. And let's just take benzene here. Let's put benzene in the middle. And if we were to take benzene and react this with nitric acid and sulfuric acid, this is the reaction we already saw, we're going to end up with a nitration reaction. Now, if instead of having just benzene, let's have toluene. So CH3, so methylbenzene or toluene. Let's nitrate it. One thing you'll notice if you were to do this reaction is that nitration with toluene occurs a lot faster. So if this is the reaction rate, and benzene is given a value just of 1, let's just make up a number. Let's say it reacts, how about 100 times faster, 10 over 2. So it's faster. And then number 2, what you would notice is that you actually end up with, oh that's pretty weird. Our toluene is that having the nitro group ortho or para to the methyl group are the major products, whereas having the nitro group meta is the minor product. So I need to squeeze a couple of other things in here. So these 2 are the major products. This one is the minor product. And this would be ortho. This would be para, back to our language of 2 substitutions, and that would be meta. So 2 things. The reaction is faster with that methylbenzene with toluene compared to benzene. And now because we already have a group on here, we have to deal with ortho meta pair. One more, and I'll put it down below with some more space here. Let's take, now rather than benzene or toluene, let's take one that already has a nitro group on it, a benzene, so nitrobenzene. And let's add a second nitro group. Same reagents. And now what we would end up seeing is that this one reacts about 10 to the 5th times slower. So this reaction is much, much slower, 100,000 times slower than a reaction with benzene itself. And here, the reaction has, let's keep the order the same as the top. Now we could end up having a nitro group being ortho, or the second nitro group added para, or the second nitro group added meta to the first one. Now what we would find is actually this meta is the major product. Ortho and para are the minor products. So it's the opposite as the case above. So this is ortho, this one was para, this one's meta. So we have to reconcile now. We have issues of rate and the regiochemistry. So the rate is everything's relative to benzene, which is just going to give an arbitrary value of 1, like 1 per second or something like that, or 1 per molar per second because it's bimolecular. What we would find is that this toluene here reacts a lot faster than benzene. Nitrobenzene reacts a lot slower. So the difference is the incorporation of a methyl group. Let's put it here for comparison. A hydrogen or the nitro group. So what this is suggesting is that this methyl group activates benzene for the reaction, so it actually happens faster. And conversely, this nitro group deactivates benzene for the reaction, so it's affecting the rate. And then the second component to think about is the regiochemistry. Why is it here on the top we end up with ortho-para dye substitution as the major product, and on the bottom we end up with meta dye substitution as the major product? So the rate is the easier one to deal with, and this is, I'll leave that there, where we can define activating and deactivating groups. The key thing to think about is that notice in the reaction that we've been dealing with all along, if we have a strong electrophile, like NO2 plus or whatever it might be, the benzene is acting as the nucleophile. What that means is that if we have a substituent on the benzene, like a methyl group, which is actually donating electron density into the ring, that should make it more reactive. So this is electron donating into the ring, and so this should make the ring more reactive or activate it relative to benzene. It's making it more nucleophilic. And it might be easier to then see the opposite case, is if we had a scenario where we have, again, the benzene ring acting as a nucleophile with our strong electrophile, like nitro or whatever it might be. Again, this is acting as a nucleophile. If we have nitro, let's just draw it out here, this positive formal charge on this nitrogen, this nitro group is pulling electron density away from the ring, or withdrawing electron density from the ring here by induction. So we were thinking about this with acid-base chemistry previously. Now if this aromatic ring is acting as a nucleophile, but this nitro group is pulling all sorts of electron density away from the ring, it should make this less nucleophilic. Okay, so by withdrawing electron density, it's deactivating the ring. So it's all about pulling or donating or withdrawing electron density from the ring. Okay, so that's what can make things be activating or deactivating. So back to the top, benzene, we're just assigning this value of 1 to make some comparisons. Methyl group is donating some electron density into the ring through induction, so it's making this more nucleophilic, so it's going to make the reaction faster. And that's what's shown on the bottom. The nitro group here seems to react much slower. When the nitro group is determined to be a deactivating group, it's pulling electron density away from the ring, making the ring less nucleophilic. So that's the idea of activating and deactivating groups. And we're going to see a couple of different groups, and they'll follow the same pattern. Okay, is everyone all right with those ideas? So it goes back to the idea of induction. Yeah, okay, excellent. So now what's up with this regiochemistry? Why is it that in the top we end up with ortho and para as the major products, and the bottom is meta? And this is where, to be, I think, hopefully a little more observant of time, why don't we go back to these slides here, and then we'll draw out the new one. What did I call it? Is it this one, I think? Oh, yeah, okay. And slide back up here. Okay, so normally we would draw these out together, but I think we're going to have a chance to draw enough of these. But let's go through it not so fast so that, because we still want it to make sense overall. So remember here, now we're drawing the other resonance structure from what we've been using before where the double bonds are, but that doesn't matter. So we're going to have our benzene ring act as our nucleophile, and the nitronium ion here is the electrophile. Here's our strong electrophile, just like we've seen previously. So this will act as a nucleophile, forming a new bond between carbon and the nitro group. And then we're going to end up here. Let's put the nitro group at the ortho position. So 1,2 di substitution. We have a carbocation, and we could draw various resonance structures, which is what's shown here in the box. So that's all good. And that's what we're going to do for each of these cases. That's the middle one here. We'll come back to that green box in a second. So the middle case here, now we're considering what happens if the nitro group is added at the 1, 2, 3, or meta attack. So the nitro group is ending up here at the meta position. Carbocation, again, it can be resonance stabilized. And finally, the same thing here if we add the nitro group at the para position. Again, form a carbocation, and we can draw the resonance structures. So those are all the different resonance structures that can form, but that alone doesn't tell us why is it that ortho and para is preferred. Those seem to be those are the major products. So what's happening energetically? And that's where we really want to evaluate the different resonance structures. And what you'll notice here is that in the top, if the nitro group is at the ortho position, in our resonance structures, one of them has the carbocation at a tertiary carbon. The one that has the methyl group of toluene. So that should be energetically favorable, because remember, we're going back to the good old days of resonance structures. It's better to have a resonance structure in tertiary versus secondary versus primary. So these are both secondary carbons, and there'll be a secondary carbocation. This will be tertiary. So that seems energetically favorable. This is probably the major control. Let's jump down to the bottom, and you can see the same thing if we put the nitro group at the para position. We have a secondary carbocation on the left, secondary on the right. However, this middle resonance structure in the green box is a tertiary carbocation. So that also seems like the major contributor. Now, when we look in the middle with the meta attack, the nitro group at the meta position, can draw just the same number of resonance structures. However, in this case, the carbocation is never situated on the carbon that's attached to the methyl group. So it's secondary, secondary, secondary. And we could go through and draw these resonance structures, and it's like it skips over that carbon. So when we're comparing these different resonance hybrids, having the nitro group, or whatever the electrophile would be, at the ortho or the para position at the bottom relative to the methyl group allows you to form a more stable carbocation compared to meta. And that should lead to ortho and para then being the major products. And we'll come back to this one in a second. And so this can be illustrated here in this energy profile, in that overall, when we were drawing those energy profiles last week, just at the very end and earlier this morning, the first step is the rate limiting step, forming this arenium ion or sigma complex. And you can illustrate this that by forming here the di-substituted compound with the nitro group at the ortho position, we have some energy barrier. And then we're just showing one resonance structure. If we form the di-substituted compound at the para position, we have also some energy barrier. However, now if we form the di-substituted compound at the nitro at the meta position, you cannot form the more substituted, more stable carbocation. So that energy barrier will be a lot higher. So it'll be much less favorable compared to these two. And so the meta attack then should be the minor product, because it takes more energy to form this less well-stabilized carbocation. So that can be used to explain having the ortho and the para being our major products. Now, one more important point here is notice when you're looking at the energy profiles in this picture that I stole from a textbook and I didn't cite, as I notice here, is that the ortho energy barrier is actually higher than the para. So go over in somewhat straight line here. And the simplest explanation for that is that having the two substituents right next to each other causes some steric interaction. So they're going to bump into each other. We're putting something here, the nitro group, which is bigger than hydrogen. So if you could put the nitro group way on the other side, that should be more favorable. So that's why the energy barrier is actually lower for the para attack. And so it comes back to a steric argument. And then last, I'm going to slide up here for a minute. Then the question is, okay, he just said that the para group in this particular case, that should be more stable because it's further away from the methyl group. But what's going on with these numbers? It looks like the nitro compound is the major product, and you get more than for the ortho compared to the para. And this is really getting to my final point and seeing Kyle's question. There's more ortho than para. Yes, exactly. So in this particular case, the reason why you end up having more ortho is because there's the probability is twice as high that you have substitution at the ortho position. In other words, there's 2 ortho carbons and there's only one para. So even though it's a little less favorable to put the nitro group at the ortho position, it's twice as likely it's going to bump into the benzene ring at the ortho position. So there's a lot of different features that go into that. However, while we're on that, there are cases where you get to a case where you, rather than having a methyl, let's say you have this big, bulky tert-butyl group here. Now, if you're going to take this big tert-butyl group and treat this with nitric acid and sulfuric acid, now, in terms of activating and deactivating, this group is donating electron density into the ring, the tert-butyl group, just like the methyl group. So this is going to be an activating group. So it reacts faster than benzene. We could draw all of the resonance structures. Let me go a little larger here. We draw all of the resonance structures when this attacks our strong electrophile. And we would find that just like we can put a carbocation on toluene, the same thing here. So this group will be known as an ortho-para director, meaning it prefers having the substituent at the ortho or the para position. However, now, because you have this big, bulky tert-butyl group, it's going to bump into the nitro group a lot more, so that now you would actually see substitution para as the major product. And then might get a little bit of the ortho. But there'd be less. And then only a small amount of the nitro at the meta position. Oh, sliding to the right. Minor. So it comes back down to, yeah, in this case, these are thermodynamic comparisons also that we're making about. And so it's a thermodynamic argument in that the energy barrier is much higher in terms of the carbocation stability to add the second group at the metal position. It's much more favorable here. And then like you were saying with kinetics, the probability is higher to bump into these two groups when you have a methyl group. However, when you make this even bigger, like a tert-butyl group, you really favor the para position. So a lot of things to consider, but let's just recap here, and then we'll show 2 more examples at least here, so that we can reflect on this today. The observation here, if you can ignore my scribbling down below, is that if we took toluene here, which I'm trying to circle, and we carry this forward in a nitration reaction, you have the possibility for 3 different products, and just assume 1 nitro group is added. The nitro group could be ortho, meta, or para. And first of all, this reaction with toluene happens faster than with benzene. So this methyl group is an activating group, would be one definition. And we can define that as an activating group by donating electron density into the ring. A little more complicated observation is this directing effect. In other words, the methyl group directs the nitro group to be ortho and para as the major product. So you want to make sure when we're talking about directing effects, and the language is an ortho-para director. Let's put it here. This is an ortho-para director. we're talking about the group that's already attached to the ring. Sometimes I know it's confusing because we'll see cases where nitro is already on the ring. So the methyl group is an ortho-para directing. It's directing the nitro group to be predominantly at the ortho or the para position. And an explanation for that is that the intermediate that you form, I'll scroll around to that slide here, the intermediate that you form when the nitro group is added at the ortho or the para position forms a more stable carbocation in the resonance hybrid relative to having the nitro group at the meta position. So since these are now more stable intermediates, they're going to be the major or the predominant pathway that the reaction follows. So that way we'll end up with a nitro group after we just take the proton off in each case at the ortho or the para position. That's preferred energetically. And then the last detail is sometimes deciding between ortho and para as the major product. It has to deal with, there's a greater probability of bumping into the two ortho positions compared to the one para position. However, if you have something really big already on the ring, you may favor the para. Okay, so I know also a lot of information, but it comes really down to carbocation stability. Why don't we look at one of the other ones that's on the slide here, and then we'll compare some other effects. So then, in response to the boss's question, if you get both the ortho and the para products as major on an exam, that's going to be okay. And so there'll be times in synthesis where you'd want maybe just the para product or sometimes the ortho ones. We'll kind of let that go for now, but I just wanted to emphasize that even though we call these groups as ortho-para directors versus a meta director, a lot of times the distribution of ortho and para is a little more complicated. So we're not going to take off points for something like that, but to recognize hopefully the difference of sterics versus kinetic effects and probability. Okay, so now